Good morning, everyone. So, in this session, we'll be looking into the how to obtain the adjoint operator given an operator. So that is very important, and we'll be seeing later on in this course that there are various operators, the Sturm-Liouville operator or eigenvalue operator that we have discussed in the last class, were basically the self-adjoint operator, and now in order to obtain the adjoint operator given an operator is very important in this course, as we see later on. So in this class we will be first defining an operator, then we will be looking into the procedure how to obtain the adjoint operator. So let us define a general operator. For example, LU is equal to 0. In this particular problem, L is the operator, and we are talking about an operator, a generalized one, a second order operator, d square dx square plus a1 d dx plus a2, which will be function of x. So in this operator, all the coefficients a0, a1 and a2, they are function of x. And let us look into the boundary condition of this operator, that, and let's say they are homogeneous at x is equal to 0 and at x is equal to 1, both u is equal to 0. So this defines the problem. LU is equal to 0 defines the problem, and BU equal to 0 defines the boundary conditions. So the boundary conditions are homogeneous, as we have discussed that if the boundary conditions are homogeneous, then the problem is posed as an eigenvalue problem. So let us find out in this operator L what is the adjoint operator. Let's see the procedure. So in order to get that, first we consider another variable v lies in the same domain, of u. Okay, so let us take the integral v L u dx, and this integration is over domain of x from alpha to beta. Then let us just expand the operator a0 d square u dx square plus a1 du dx plus a2 u is equal to 0, a2 u multiplied by dx, and then we write v a0 u double prime plus a1 u prime plus a2 u dx, where primes denote the derivative with respect to x. So u double prime is nothing but d square u dx square, and u prime is nothing but du dx. Then what we will do, we will be expanding. We open up this brace, and v a0 u double prime dx plus integral alpha to beta v a1 u prime dx plus alpha to beta v a2 u dx. Once we write this, then what we will do next is that each of this integral will be integrating by parts, considering the first part as the first function and double prime as the second function. In this integral, va1 as the first function, u prime as the second function. So let us solve this equation by opening up the integration by parts. So if you really do that, what you will be getting is that alpha to beta vlu is equal to first function va0, differential of the integral of the second function, so it will be u prime from alpha to beta minus differential of first function v a0 prime, integral of the second, so u prime dx. So that will be the first one. In the second integral, again we do first function va1, integral of the second one u alpha to beta minus differential of first function, so v a1 prime integral of the second function alpha to beta and the third integral remain as it is, alpha to beta v a to u dx. So let us collect these terms. So this becomes VA1 VA0 u prime plus VA1 u. This will be evaluated from alpha to beta minus again we integrate it by parts. So this will be the okay, before that let us consolidate this one. So this will be v prime a0 plus v a0 prime u prime dx minus alpha to beta v prime a1 plus v a1 prime u dx plus v a2 u dx. The next we will be doing integration by parts, again considering this is the first function, these are the second function. So I write the equation as v a0 u prime plus v a1 u lying between alpha to beta. Now first function integration of the second one, so it will be v prime a0 plus v a0 prime u alpha to beta minus plus differential of the first function integral of the second function alpha to beta. So differential of first function will be v double prime a0 plus v prime a0 prime plus v prime a0 prime plus v a0 double prime u dx plus integral alpha to beta v a2 u dx. Now let us see what we get. So we collect this term first. So this will be a0 v u prime plus a1 v u minus a0 v prime u minus a0 prime v u. This will be evaluated between alpha to beta, and we call this part as bilinear concomitant, and its notation is JUV, and then we collect the term. So this becomes plus alpha to beta v double prime a0 plus v prime a0 plus v prime a0 prime plus v a0 double prime minus v prime a1 minus v a1 prime plus v a2 u dx. In fact, this is the first term. In fact, we should write this term as well. So in the previous step, that is missing v prime a1 plus v a1 prime u dx plus this. Okay, fine. So now let us see what we get. We get alpha to beta VLU is equal to nothing but JUV plus alpha to beta. What we will be getting is A0 V double prime plus 2 A0 prime minus A1 V prime, okay, plus A0 double prime minus A1 prime plus A2 times V multiplied by U dx. Okay. So, we will be getting A0 prime times V. So, A0 prime times V, there will be, it will be occurring twice. So, it will be 2 A0 prime, and you will be getting this. So, ultimately this can be written as JUV plus alpha to beta U L star V dx, where JUV is known as bilinear concomitant and its value is A0 V U prime plus A1 V U minus A0 V prime U minus A0 prime V U evaluated at alpha and beta. And if you remember that original boundary condition was that at x is equal to alpha, u was equal to 0, and x is equal to beta, u is equal to 0. So, all these three terms will be gone, only this term will be surviving. So, it will be A0 beta v at beta u prime at beta minus A0 at alpha v at alpha u prime at alpha. So, now we can select the boundary condition of the adjoint problem. So, the adjoint problem is basically the problem associated with V. So, adjoint problem is problem associated with V. So, therefore, we have to, if we select at x is equal to alpha and beta, if we select V is equal to 0, then your bilinear concomitant will be equal to 0. That means, we can select the boundary conditions on the adjoint problem V, so that the bilinear concomitant will be equal to 0. Now, let us look into the L star, which is nothing but the adjoint operator of L. So, what is L star? L star is nothing but adjoint operator of L. So, therefore, this L star is A0 x d square dx square plus 2 dA0 dx minus A1 times V plus d square A0 dx square minus dA1 dx plus A2. So, this is the adjoint operator, and we can clearly see that adjoint operator is not equal, L star is not equal to L in this particular case. So, L star is not equal to L, but B is equal to B star. That means, both the boundaries of the original problem U, which was basically nothing but the combined into the boundary condition B, that at x is equal to alpha and beta, u is equal to 0, and we have selected for the adjoint problem V same boundary condition at x is equal to alpha and beta, V is equal to 0. So, B is equal to B star. B star is the boundary condition associated with the adjoint problem. So, but L is not equal to L star. So, this problem is not a self adjoint problem. Operator L is not self adjoint if L is equal to L star and B is equal to B star, then we will be having a self adjoint operator. Operator and self adjoint problem. Okay. So, we just look into one example that L is equal, let us consider a Laplacian operator in one dimensional d square u dx square, okay, and differential. So my operator is Laplacian in one dimensional, so d square dx square is my operator, and let us look into the boundary condition, differential boundary condition. So differential boundary condition is at x is equal to 0 and x is equal to 1, let us say u is equal to 0. Now let us find out what is L star and what is B star in this problem. So this condition, boundary condition, is nothing but the B of the original problem. So what we do next is we carry out an integration v times L u dx from 0 to 1, where v is a variable in the same domain as u. So therefore it is becomes 0 to 1 v d square u dx square is equal to into dx. Okay. So then we integrate by parts. This is the first function, integral of the second function 0 to 1 minus differential of first function, integration of second function dx from 0 to 1. Then again we do integration by parts here. So this becomes v du dx from 0 to 1 minus first function dv dx, integral of the second function u 0 to 1 minus minus plus differential of the first function and integral of the second function. Okay. Now let us collect terms and see what we can do about it. So integral 0 to 1 v L u dx in this particular case becomes v du prime dx minus u v du dx minus u dv dx evaluated from 0 to 1 plus u d square v dx square dx. Okay. So let us put the boundary conditions. So this is v at 1 du dx evaluated at 1 minus u at 1 dv dx evaluated at 1 minus v at 0 du dx evaluated at 0 minus minus plus u at 0 dv dx evaluated at 0 plus 0 to 1 u. So this is now my L star v dx. So as we had the boundary condition B, u at 0 is 0, u at 1 equal to 0. So therefore the bilinear concomitant remains only two terms. We do not have any idea about u prime at x is equal to 0 and x is equal to 1. So therefore we have to, if we select at x is equal to 0 and x equal to 1, v is equal to 0, then this bilinear concomitant term will vanish. That means if we select B star as at x is equal to 0 and 1, v is equal to 0, then bilinear concomitant terms will vanish, and what we get is v L u dx 0 to 1 is nothing but 0 to 1 u L star v dx. Now let us see what is L star. If you look into this L star is this. So L star is nothing but d square dx square. This is same as L, and B we have seen that this same as B star. So Laplacian operator is a self adjoint operator with the differential boundary condition. So d square L is equal to d square dx square is a self adjoint operator okay, with differential boundary condition. Now let us look into the problem. If the boundary condition is changed to Neumann or Robin mixed, whether my the adjoint problem is self adjoint or not. Now let us just go into two quick example. that L is same as one dimensional Laplacian, but the boundary conditions are now changed. At x is equal to 0, we have du dx is equal to 0, and x is equal to 1, we have, let us say, u is equal to 0. So, let us integrate v L u dx, and ultimately what we will be getting is v du dx minus u dv dx evaluated from 0 to 1 plus integral u d square v dx square dx. So, all the algebra remains same. Now, it will start showing difference from this point on. Let us evaluate the bilinear concomitant first. V at 1 du dx at 1 minus u at 1 dv dx at 1 minus v at 0 du dx equal at 0 minus minus plus u at 0 dv dx at 0 plus u L star v dx. So, at x is equal to 0, du dx equal to 0. So, this term will be off. At x is equal to 1, u is equal to 0. So, this term will be off. Now, if we select that, so we do not have any idea about du dx. So, but if we select v at x is equal to 1 and dv dx at x equal to 0, then this bilinear concomitant will be 0. So, therefore, at x is equal to 0, my dv dx is equal to 0 and my x is equal to 1, v is equal to 0. So, that will force my bilinear concomitant to vanish. So, if we look, so this is the same problem as B star. So, this as B. So, this boundary condition B star, and if we see that B star is equal to B, and this problem now becomes V L U dx is equal to u L star V dx, where L star is equal to d square dx square is equal to L. So, L star is equal to L, B star is equal to B. So, again it is a self adjoint operator. So, d square dx square is a self adjoint operator with Neumann boundary condition. Now, we will be redoing this problem once again by considering a Robin mixed boundary condition at x is equal to 1, and we will show that again the one dimensional Laplacian is a self adjoint operator. So, let us go for a third example quickly. We have the same Laplacian one dimensional as the operator d square dx square, and b will be at x is equal to 0, u is equal to 0. At x is equal to 1, I have du dx plus beta u is equal to 0. So, we have the Robin mixed boundary condition at x is equal to 1. Now, again let us look into the integral v times L u from 0 to 1 dx. So, this will be having let us look into this form v du dx minus u dv dx from 0 to 1 plus u d square v dx square dx. Now, we evaluate the bilinear concomitant term. So, let us find out what is j u v in this case. J u v in this case will be v at 1 du dx evaluated at 1 minus u at 1 dv dx at 1 minus v at 0 du dx at 0, and then minus minus plus u at 0 dv dx at x is equal to 0. Now, we have already in the boundary condition that x equal to 0, u is equal to 0. So, at x equal to 0, u is equal to 0. So, this term will be off. Now, at x is equal to 1, du dx is nothing but minus beta u. So, at x is equal to 1, we write du dx as minus beta u evaluated at 1. So, minus v at 1 beta u at 1 minus u at 1 dv dx at 1 minus v at 0 du dx evaluated at 0. Okay. So, we take u at 1 common minus u at 1 common. So, this becomes dv dx plus beta times v evaluated at x is equal to 1 minus v at 0 du dx evaluated at x is equal to 0. So, in order to make the bilinear concomitant to vanish, I select the boundary condition at x is equal to 0, v is equal to 0, and at x is equal to 1 I have dv dx plus beta v is equal to 0. So, these are same as b. So, b star is same as b in this case. So, b is equal to b star. If I select this, then my bilinear concomitant will vanish, and I will be having integral 0 to 1 v lu dx is equal to u L star v dx, where L is equal to d square dx square is equal to L star. So, L is equal to L star, b is equal to b star. So, this problem, the operator, the one dimensional Laplacian is a self adjoint operator. Even you have a Robin mixed boundary condition. So, we have already seen that the Laplacian operator is a self adjoint operator irrespective of the boundary condition, whether there is it's a Dirichlet boundary condition, whether you have a Neumann boundary condition, whether you have a Robin mixed boundary condition. So, in this class whatever we have seen is that let us summarize. We know, given an operator, a general operator, how to obtain the adjoint operator, and during the derivation of the adjoint operator, the boundary conditions will appear as a combination of terms which is known as the bilinear concomitant. By selecting appropriate conditions on the adjoint problem, adjoint variable v, we can select the boundary conditions on v and can force the bilinear concomitant to be 0. Thereby, we will be obtaining the conditions on the adjoint problem v, and similarly we will be getting the adjoint operator L star. If L is equal to L star and b is equal to b star, then we will be having a self adjoint problem, and the operator is the self adjoint operator. And we will see in the next class that the Sturm-Liouville operator or the standard eigenvalue operator is a self adjoint operator, and we will be looking into some of the properties of the self adjoint operator. Then we will be ready for doing a separation of variable type of solution for partial differential equation. Thank you very much.